Mastering search algorithms. From basic traversal to advanced heuristics, the world of search algorithms forms the backbone of artificial intelligence, optimization problems, and even web technologies we interact with daily. Whether you're solving mazes, recommending products, or navigating complex data structures, efficient search strategies determine performance and usability. Understanding these algorithms isn't just theoretical, it shapes real-world applications. From Google's PageRank to route-finding systems like GPS navigation, mastery of search techniques empowers developers to create smarter solutions. Fundamentals of search problems. A search problem consists of states, actions, transitions between those states, and goals. Agents navigate state spaces by applying operators to transform current states toward desired outcomes. The choice of search strategy depends on factors like space complexity, time efficiency, and whether full knowledge exists about the environment. These constraints define whether breadth-first or depth-first approaches might be optimal. State representation defines how environments are modeled mathematically. This could range from simple graphs to multidimensional matrices depending on application domain. Example: in chess, each board position represents a state, while moves correspond to transition functions producing new game states. Initial state, starting configuration before any operations occur. Goal test, function determining if solution has been reached. Path cost, metric quantifying resource consumption during traversal. Uninformed search strategies. These blind search methods explore state spaces without prior knowledge of goal locations. Their effectiveness relies purely on systematic exploration patterns. Breadth-first search, BFS, guarantees finding shortest paths in unweighted graphs by exploring nodes level by level. It maintains queue-based processing order. Depth-first search, DFS, prioritizes deep exploration along single branches until reaching dead ends. This approach risks missing optimal solutions entirely. Cyclic behavior becomes problematic in DFS unless implemented carefully. Maintaining visited node tracking prevents infinite loops in recursive implementations. Differences manifest clearly in memory usage. BFS requires storing entire frontier layers, whereas DFS keeps minimal stack overhead. Informed search techniques. Heuristic guided searches leverage domain-specific knowledge to prioritize promising pathways. This leads to significant improvements over traditional blind search methods. Best first search selects next node based solely on heuristic estimates rather than actual path costs. While faster, it lacks guarantee of optimality. Admissibility, a property describing heuristics that never overestimate true costs. Admissible heuristics ensure eventual discovery of optimal solutions. Consistency, stronger condition requiring heuristics to satisfy triangle inequality properties between neighboring nodes. The power of A**. Combining cost and heuristics. A** algorithm balances exploration and exploitation by combining actual path costs with estimated remaining distances to targets. Its versatility makes it widely applicable across domains. Formula: F n equals G n plus H n G n cumulative cost from start to current node nh. N estimated minimum cost from end to goal. This dual component evaluation enables smart decision-making while retaining mathematical rigor in solution guarantees. Evaluating algorithm performance metrics. Time complexity measures computational effort relative to input size. For tree structures, branching factor significantly impacts execution speed. Space complexity refers to memory requirements for maintaining explored/queued nodes. Some algorithms trade off space efficiency for better time performance. Optimality criteria vary. Greedy best first may find good solutions quickly but doesn't always identify globally optimal ones. Completeness indicates whether algorithm will eventually find solution if one exists. Not all methods guarantee success in infinite state spaces. Applications beyond traditional problem-solving. Search algorithms power recommendation engines by analyzing item relationships in vast graph networks. Netflix suggestions rely heavily on optimized traversal techniques. Autocomplete features utilize modified search patterns to predict likely completions based on partial inputs. This involves sophisticated pruning mechanisms. Robotics employs hierarchical search frameworks for simultaneous motion planning and obstacle avoidance tasks. Multi-agent coordination adds another layer of complexity. Web crawlers implement intelligent traversal strategies to efficiently index billions of interconnected pages without redundant visits. Challenges in modern implementations solving complex problems often requires handling enormous state spaces that exceed available memory capacity. Approximate methods become necessary in such scenarios. Real-time constraints demand lightweight implementations that balance accuracy with responsiveness. This applies particularly to embedded systems and mobile devices. Dynamic environments require adaptive algorithms capable of modifying search behaviors based on changing conditions. Maintaining consistency across distributed systems introduces synchronization challenges that must be addressed through consensus protocols. Future directions and emerging paradigms. Quantum computing promises revolutionary changes in search capabilities by leveraging superposition principles for parallel computation. Reinforcement learning combines trial-and-error approaches with reward maximization objectives to develop autonomous searching agents. Federated learning architectures enable collaborative search efforts across decentralized data sources while preserving privacy constraints. Neural network integration allows pattern recognition abilities to enhance traditional search methodologies in novel ways. Practical considerations for developers selecting appropriate data structures is critical for implementing efficient search routines. Priority queues prove especially useful for **-based implementations. Tuning heuristic functions appropriately ensures both effectiveness and efficiency. Too optimistic estimators risk poor performance despite admissibility guarantees. Testing with various benchmark problems helps validate implementation correctness against expected behavior specifications. Profiling tools assist in identifying bottlenecks and optimizing algorithmic performance characteristics effectively. Conclusion: from foundational traversals to advanced heuristically guided explorations, search algorithms form the bedrock of modern problem-solving paradigms. Mastering these concepts unlocks powerful capabilities across diverse fields. As technology evolves, continuous refinement of existing techniques alongside exploration of emerging approaches remains vital. Practitioners should remain adaptable while grounded in core algorithmic principles.